While the mic is coming to you, I'm going to take advantage of my role as chair and ask you a question. So, of course, I come at this from a politics and law perspective, outer space law. And I love that you ended with who we are. I wonder, as a scientist working on the ground, how you feel about other entities that are starting to express interest in Mars. So, for example, the United Arab Emirates, China, also non-governmental organizations like Mars One. Do you guys see them as potential collaborators or as rivals, or...?
So certainly the planet is not for anyone's taking, right? It's for everyone. So in that sense, I think the only way that we're going to be able to get humans to Mars is to do it as sort of a global endeavor, for sure. Both from a technology perspective, from a funding perspective, from a political will perspective. It's going to have to be kind of a universal endeavor. So the fact that more people are getting involved, I think, is a great thing. So
great. I love it that you mentioned the JPL thing. I'd heard that, but I wasn't sure if it was true or not. Yeah. I have confirmation now. Brilliant.
Hi. With regards to the methane calculations, could the SAM instrument differentiate between carbon-12 and carbon-14? Because I know with Beagle 2, that was a key thing about their mass spectrometer.
Oh, like so for isotropic ratio purposes? Yes. I'm not actually sure. So I was more on the EDL side as opposed to the instrument side. But I think if you go to the website, you'd be able to look up the details of the SAM instrument. So I do know that one of the ways that you can make the determination of geological versus biologic ratio is to look at different ratios and specifically look at methane versus ethane. So if you have that ratio, then you can use an Earth-based analog to say, oh, this is geological, this is biological. They can get some isotopic information, maybe by correlating it with the elemental signatures, but I'm not sure about that. So you'd have to look up that online. So I know that my understanding is they don't have the ability to determine whether it's from this source or that source. So, but that's a good point. And I think, yeah, the more sophisticated measurement you can make, the more questions you can answer like that. So,
can we go here, and then when you're done, if you could pass it just down to the gentleman in the dark jacket.
With regards to the beyond part, what could you say about the 2020 mission? Because I know that the next one's coming up in 2020, so just in 4 years from now.
Oh, so ironically, there's two 2020 missions. So ExoMars has a 2020 mission, and NASA has a 2020 mission. And I was just at a workshop this past week where I think it was Franco Ungaro was up talking about ExoMars 2020 and ExoMars 2016. And so his analogy, which I thought was a nice analogy, is that the 2020 NASA rover is more geological science in nature, whereas the ExoMars 2020 rover is more biological in nature. So I think they're both being planned. I think they're both well-funded. The Mars 2020 mission uses a very similar EDL architecture to the one that we used for MSL. So that's in relatively good shape in terms of moving forward. So I think they're well-funded and they're well on their way to meeting those both science and launch date targets. So these are good times.
Oh, you got it. Okay.
You mentioned that the power source on Curiosity is radiation-based, which is an advantage over Spirit and Opportunity. But what do you think about the ethics of bringing a highly radioactive source with an enormous half-life onto a planet that has not yet been conclusively where life has not conclusively been disproved?
Well, it's not highly radioactive. So plutonium-238 actually has a relatively low radiation level in that sense. So you can actually kind of hold it in your hands if you wanted to. You shouldn't, but you can. So I think from that perspective, so we actually go to great lengths to protect the planets that we visit. So we actually have something called planetary protection, which is covered by all space agencies, just not the United States. So our biggest concern for planets that we may be visiting that may have potential life is actually contaminating them with biological contamination such as bacteria. So we actually go to great lengths to make sure that our spacecraft are clean, and we actually cook our spacecraft to basically destroy any bacteria or bacterial spores that are in them. So that is definitely, we're very cognizant of what impact that could have, and so that's one of the things that we do to make sure that doesn't happen. But from that perspective, not really. It isn't as bad as maybe as what you have been, you've heard or been told, but you can actually read up online as to what the levels are for plutonium-238 versus other radioactive substances, but it's actually pretty benign. And the reason why, and the fact that it is so benign means that it goes over a long period of time, like 70 years kind of thing, so it's generating only a little bit of heat. So you're just converting the heat into electricity by using a thermocouple, using the thermionic effect. But everyone has their own opinions. That's my opinion. Good point, though.
Could we have this young lady here, and then we'll come back over here.
You said earlier about the rover going really slowly. Is there a particular reason for that, or is it just that the technology is not very good at the moment?
So there is a particular reason for it, and it's because we have to have hazard avoidance, and to be able to have hazard avoidance, we have to collect images, and then the onboard computer has to process those images. And so right now, it's actually the computational speed of the flight computer which actually drives it to be that slow. So it can't actually go any faster because it can't process the images fast enough. So space-based computers are very different from like commercial computers, so they're probably like 10 to 15 years apart in terms of capability level, in terms of processor speed. But the reason why it's not a problem, however, is because we don't need to go that fast, because we really, the day one of science isn't getting to Mount Sharp, it's every day that we go there. So we don't really need to go any faster because we're always collecting science, and that's usually a slower activity than actually driving to the next place. But if, for example, your primary purpose was to only go to point B, for example, to resupply some human colony, then you would want to be able to go faster. But at that point, we would just have to come up with, we would just have to qualify basically a faster computer. And certainly commercial computers do exist of incredible speeds, as we all use, and so that would just have to be something that happens, which I think it can and would. A good question.
I believe I had someone over here, and then I'll come back to some of our younger members on the left here.
You mentioned methane, which possibly could originate from life and maybe just geological. But what about amino acids? Are you looking for them? And if they were there, do you have the capability to identify them?
I think it probably depends upon the length of the hydrocarbon chain. So I think the longer the hydrocarbon chain gets, the more difficult it is to detect. And so in terms of the building blocks of amino acids, like in terms of like carbon, nitrogen, hydrogen, oxygen, all of those things have been detected. But I think the signature for like really complicated amino acids could be quite long. So unfortunately, because my background isn't on the science instruments, I can't tell you like the specificity of how big of a chain that it could do, but certainly is there to detect organics. But I think like, for example, on I think it's Titan, they have something called tholins, and tholins are like these incredibly long hydrocarbon chains, so you'd have to have a very sophisticated mass spectrometer to be able to detect that. So, but certainly we can detect all the building blocks of organics, and there's probably a length to how big of an organic that we can look at. And I just don't know what that is off the top of my head. But I would say that you can find all that information in the public domain for that particular instrument, which is the Sample Analysis on Mars instrument.
We've got two younger members of the audience over here who have questions. We can start with the fellow there and then go a couple rows back.
You said what the actual strings were made out of, Kevlar, but what's the actual parachute made out of?
Oh, so the parachute, these parachutes are slightly different, but for analogy purposes, in terms of the shape, they're very similar. So this material for us is made out of nylon, so it's kind of like the material that your backpack is made out of, but very thin, very strong nylon. And then the lines are also made out of thinner Kevlar, and then there's typically a big bridle, which was being passed around before, which is also made out of Kevlar. So we usually use nylon and Kevlar. So nylon for kind of the soft, flexible part of it, and then the structural grid that goes between it, we usually use Kevlar.
Good question. I wondered that as well. And back up to this fellow here.
Are you planning for the first people to go to Mars to service the Mars rovers?
Oh, are we planning for them to service the rovers? I don't know. That's a good question, because at that point in time, depending on how late it is, they may or may not be functional still. So I think if they landed to a place close enough to them, they might be able to utilize their spare parts, for example, like Mark Watney did in The Martian, but we probably would also bring our own new rovers with us to do those kinds of things, and there'll be more rovers subsequent to that. But it all would depend upon if the landing site that we selected was close enough to them or not, because if it wasn't close enough, then we probably wouldn't, but if it was nearby, I guarantee you we would want to go and check out and see how they were.
And come to this gentleman here. While the mic's coming over, just out of curiosity, this is not a very nice question, but do you have any sense of when you think there would be a manned mission on the cards?
So that's interesting. So I was just at a workshop this week where that was discussed, and so the timeline is for, I think it's mainly driven by finances and political will, but I think the timeline there they presented was like late 2030s, which isn't that far off.
Whoa,
but that would require obviously a lot of funding.
Sure.
And international support to make that happen.
Yeah.
It wouldn't be done just by a single space agency for sure. But from a technology perspective, we still have a little ways to go, so that technology has to be developed first, which is an extension of what we've already done, but it is more difficult because, I guess one thing I didn't say is that, so when you're coming in to land initially, when you're coming in at hypersonic speeds, we actually used, and I did bring it here, I just forgot to mention it, so even though this ugly looking shape doesn't look like it would generate lift, it actually does generate some lift if you keep it at an angle of attack. So what was unique about the MSL mission is that we did have it at an angle of attack, so it had a lift to drag ratio, and that we had thrusters on the outside that were used to rotate the craft and then modulate its bank angle. So we were actually flying down like this as a means of increasing our downrange distance and as a means of actually reducing the total load that the vehicle would see from a mechanical perspective. So that's why I have my analogy of an airplane here. And so for a human entry, you would actually use like a lifting body trajectory like this, and it would even be better than this one. So you'd have more lift to drag. And so that's a technology which we started with this mission, but we need to increase even further to be able to increase the landed mass. So for order of magnitude reference, you know, our entry mass is like 3,000 kilograms. A human mission to Mars is an order of magnitude higher than that. And it requires a larger space because you're not just carrying a rover, you're carrying people. So that's also another challenge that has to be developed.
We're going to go over here. And moving on with the diversity theme, are there any women? That would be great.
Two questions for you. As an aerospace engineer, what do you think the prospect would be of using aeroplanes or airships in the Martian atmosphere? And the other one is, we've seen things by Buzz Aldrin where he's thinking of people of my generation going on a one-way trip to Mars with no prospect of coming back.
I don't see the gentleman. Oh, I'm sorry. Okay, so the first one was airplanes on Mars. And so we actually are planning a helicopter demo for the Mars 2020 mission. So that's actually something that we are planning to do. So that's not quite an airplane, but it's kind of a, you know, it's kind of like an airplane. So it certainly is a thing that you can do. It would be a nice thing, like after you landed, you would have a little airplane that can go and do reconnaissance things and things like that. So that's what this helicopter is, and it's called, oh my gosh, Leonardo is the name of it. So it's going to be a payload on board the Mars 2020 rover. So it can definitely be done. Yes, the atmosphere is thin. Yes, you have to have a big wingspan, but it can't weigh that much. And then I think the second thing was, another thing you could actually do, which isn't an airplane, but you could use like a guided parafoil, which is more of a lifting parachute type thing, as a means of getting you more precise landing. So that's something that's definitely being studied. One-way trip, I think that's more of a catchy thing to make it sound like super risky, but we wouldn't do that. It just doesn't make any sense. So from a technology challenge, so my very first job, my initial background was actually in the development of launch vehicles and propulsion systems for launch vehicles. So my personal opinion as a aerospace engineer with a propulsion background is the technical complexity of a launch vehicle on Mars is actually far, far lower than a re-entry vehicle on Mars. And the reason for that is because you're using the atmosphere to slow yourself down. So you have all these bizarre aerodynamic effects that you have to take into account. You have the aerothermal heating, which you have to take into account. For a launch vehicle going through the atmosphere, you're dealing with 1/3 the gravity compared to an Earth-based launch vehicle. You're dealing with much lower drag compared to an Earth-based launch vehicle. So that's actually a much easier technology to develop. So I take issue with the premise that that's something we'd even do, because we know we can actually do that relatively easily compared to the other things that we have to do. So, but that's my opinion, because that's my background.
I've asked this question as well, and I've been told that governments would really not go one way because of the care of duty and that sort of thing. But when you have these organizations like Mars One, I think there's interesting ethical questions about what regulation we have over them and what they could sort of get away with. Do we have a microphone up?
Thank you for a wonderful presentation. Breathtaking engineering. You mentioned the dust. I know there's big storms on Mars. How do you keep the lenses of the cameras clean, or doesn't that matter because you've got a big depth of field or whatever?
Well, it does matter, and I think that's a good question. So I think if you've got a horizontal surface platform, dust is more of an issue than a camera, which is kind of vertical to it. So just from the perspective, there isn't that much stuff that gets on it. So that hasn't been a problem. However, during the landing event, we did have covers. So during the landing event, you've got the plumes coming down, interacting with the surface soil, which then comes up like this and just basically blasts where those camera locations are. So there, we actually did have camera covers on. So the very first image that I showed you was after the camera covers came off, but there was an image between that where you could see how much dust had deposited. So you do get some, but you get a lot less with a sort of a vertical plane versus a horizontal plane. But, if you needed, so that's pretty much, it's the geometry that helps you, because the landing event is a unique case where we do have covers, but the dust deposition that you get from winds usually doesn't impact them as badly, based off of our experience too.
Can I go up to the lady in the blue sweater, and then I'll come down to this gentleman here.
Great questions, by the way, everyone.
Hi. In the Martian, obviously, there's the massive sandstorm that causes them to abort the mission. Is that something you could plan for during your EDL sequence, or was that something that would just cancel the mission?
So that was a flaw in the movie.
Oh, okay.
So yes, you actually do get high winds on the surface, but the density is super low, so you don't get the aerodynamic force that they showed. So it was the premise of the movie, which I think the author would admit that he didn't get it. He had to have some reason to have things go wrong, and that was one of them. So that's what that is. So we do know what the winds are. They are really strong. They can get up to 50 meters per second, but it's at 1% the density. So it's not that big of a deal. So it gets dropped down because of that. So not really, you don't have to worry about that too much. But you could also have a more stable platform, and you would design it for your worst case scenario for sure. And then, so they actually, since you're about this topic, I'll say it. So my big issue with The Martian, the premise of The Martian, was, this is a really dumb one, but I just got annoyed with it in the first couple of pages. I love the book, don't get me wrong. I thought it was a great book, was that the fact that they would have no redundancy in their telecommunication system. That's ludicrous. So they had the one dish, it's gone, we're toast. That would not happen. So our little rover has a low gain antenna, 2 low gain antennas and a medium gain antenna. It has the ability to communicate with orbiting assets and direct to Earth. So that's the reason why that premise, I think, was flawed. But it was the premise of the movie, so that's why they did it.
So weather isn't an issue on Mars for any mission?
Not in that sense. So this is an interesting aside, which is that the dust storms at altitude actually do affect the density profile on Mars. So we choose to not usually go in during dust storm season because it adds more variability to the density profile. If you don't know what your density profile is, you don't really know how you're going to perform. Your landing ellipse is going to get bigger. So if you can avoid the dust storm season, you would. And then the other thing that you could think about is that if you have dust particles, we don't know actually, like maybe they would interact with the heat shield material and potentially cause some havoc, but we have typically avoided going during dust season because of the variability in the atmospheric properties. Oh, and I would say that the rovers, which have had solar panels, unfortunately, that has deposit on the top of them, which then means their power over time decreases.
Hello.
Good question.
Sorry. Hi. I'm an aerospace engineer too, and I actually work on high-altitude drones. I was wondering, why would you use a helicopter versus a fixed-wing aircraft? And number 2, what do you think about SpaceX's prospects of landing on Mars by 2025?
So I wasn't part of that engineering trade, but my guess is that it's driven by the science that they're trying to do. So if they're trying to do imaging in like sort of a fixed location, the ability to hover would probably give them a better science return. So that's my guess as to what it's driven by. And then from a controls, the people I know who are working on it are more in the controls area, so maybe they probably get more control over what it is that they're trying to image. So that's my guess. But it's also like a technology demonstration thing. And they also only have the need to go very short distances away from the craft, because it's probably battery powered, so they have to be able to come back. So it's more architecture dependent. It doesn't mean that you couldn't do an airplane, for example. I think you could. But then you would have a different mission architecture that you would probably go somewhere, stay there, and maybe never come back, right? Because you'd have to have enough power on board. So you always have to do that trade, right? So if your mothership has communications, your mothership has your power, and you're just going away from the mothership, coming back, that's different than if you are your own mothership. Oh, the SpaceX question. So I think that, so in general, the commercialization of space is fantastic. Getting private sector money in is fantastic. I think he's probably going to push it as far as he possibly can, right? Because I think he has the finances, or the company has the finances and the will to do it. There's a lot of challenges involved, and my guess is the company will work closely with NASA as part of that as well. So, but I think it's a great thing. So people ask me that all the time. So I mean, for sure, there's no reason why it should be restricted to one governmental body versus another one. I mean, if you take it, for example, the aircraft industry, right? At some point, maybe it was all government, now it's not, and now people get to travel everywhere. So I think that's the way that you can commercialize space, by having more private individuals investing in the process, so.
Can we come back up here to these two, and then I'm going to come back over here to this young man.
You said a lot of CO2, carbon dioxide, there on Mars atmosphere. Yes?
Yes.
So the essential process of life is photosynthesis. Without photosynthesis, we cannot get life. So it is an opportunity to plant or cultivate plants there. And then a lot of plants will be developed there. That is one point. The other point, I'm asking, it must be life there. The life must be an anaerobic life because there is no oxygen. There should be an aerobic bacteria because it doesn't need oxygen to survive. I don't know. What do you think of?
So I don't think to date any instrument has been sent which has the capability specifically to detect life. That's a different type of instrument. So we don't have the data to answer that question. But from a hypothetical perspective, you're right. If you have something like bacteria which can utilize CO2 to generate energy, or algae that can do that, or plants that can do that, then at some point in some future mission, it would be nice to try and send them there. And there's something called extremophiles, which I think the student over there, who I don't know if he's there anymore, mentioned, is that if you can bring things like that there, then maybe they can also produce oxygen. So yes, hypothetically, I think what you're saying is correct, but because we haven't made that kind of measurement, we just don't know the answer to that question.
Thank you very much for a fantastic talk. It was great.
Thank you.
Considering how light the parachute and how small you can dense it to, why did you not make it much, 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 much bigger?
That's a good question.
And where is Curiosity going to go after the mountain?
So the reason why is, there's a simple reason why, is that we already made it much, much, much bigger from the last one. And so when you make a bunch of changes from a prior design, you do have a certain nervousness as to whether or not it's going to work. And so we knew, you start off with a set of requirements, so we knew what we needed. And so that size was actually what we needed to be able to be successful. The other reason why is that the way you deploy a parachute, on Mars at least, or supersonically, is you deploy it using a mortar, which means you push it out. And so there's only a certain size parachute that you can actually push out with a mortar. Otherwise, you have to pilot deploy it, which means that you have a little parachute which is deployed by a motor that then pulls out a bigger parachute. But because we've never done that supersonically, we didn't want to do it. So in order to be able to go with a bigger one, you probably would have to have a pilot deployed chute, but that technology didn't exist at the time. And so it's all about, you know, building on what you've done before. So if you want to do something completely different, then you have to spend a lot of money to do the completely different thing. That being said, there is a program which is ongoing now, which is called LDSD, Low Density Supersonic Decelerator, where part of that program, which is a technology demonstration program, was to qualify a balut, which is a high Mach little parachute, which then could be used potentially to pull out a large one in future. So that was sort of like follow-on technology development work that happened. But it's really driven by size, the ability to deploy it, and our experience base operating a certain aerodynamic regime. But this one was much, much bigger than the one we had done previously. So, and that was where we decided to call it quits at that size. Oh, what was about Curiosity? Where it's going to go to next? Oh, yeah. I mean, I think it has so much to explore, right? It's only just started exploring sort of the reaches of Mount Sharp, so it's just going to keep on exploring that region. So I don't think it's not going to leave the crater because it can't leave the crater because it can't get out from the crater. So it'll probably just explore more regions there, and will go for as long as it can. Because as long as it's surviving, and as long as it's able to collect the science data, it just collects more and more science data. And each location that it moves to, it sees something very different. And so the science data that comes as a result of that is also completely new. So even Opportunity, who's been driving around since, 2003, I mean, it's still going, right? And so it hasn't run out of things to see in its location. So I think there is far more science locations for it to see than it will last, given where it is.
Hopefully it'll outlast its sell-by date, but do you guys have an estimate of when
Well, so our mission life was only 2 years, so it's already exceeded that.
Okay,
so.
okay, incredible.
Hello. Early on, you had these bouncy balls, didn't you, where they came down and then they bounced 27 times or something before they actually came to rest. Now you've got this sky crane thing. Have you got any other wacky ideas for landing on the surface of Mars?
That are wackier than the sky crane?
And if you were going to send humans there, what method would you use? Because obviously you can't decelerate too quickly because then they would pass out because of the G's. So What do you think?
So in terms of the wacky thing that we did before was airbags, and so it did bounce around. And the reason why we picked that is because it was actually a pretty robust way of doing things, because you didn't really care about what your orientation was. The shock was absorbed by the airbags. So it was a good way of doing things, but airbags actually also have a technology limit. So the mass that MSL was too high for existing airbag technologies. So we're like, do we develop new airbags, or do we something different? Now the disadvantage of airbags is that you have to carry that mass with you all the way to the ground. You end up bouncing around all over the place, which gives you more uncertainty on where you're going to end up. Then you have to come out of the airbag. You don't know what your orientation is going to be, so then you have to have a mechanism which writes yourself to the orientation you want to be. All of that takes away mass from the science payload and puts it just on this landing system. So the Sky Crane landing system was actually more mass efficient, which means that you carry less mass to do your landing, more mass to do science. That's the reason why it's better. It's more complicated, which means it has more potential failure modes, which means you have to test and understand. But that was kind of the reason why we picked it. The other reason why we picked it in terms of going propulsively all the way to the surface was to increase the distance between those rocket engines were. Because if you take your garden hose and you fire it into a sandbox, what happens? Sand goes everywhere, right? But if you stand further and further away from the sandbox with your garden hose, less sand gets kicked everywhere. And so that's the reason why we use the Sky Crane mover, because it actually keeps you further away from the sandbox so that you generate less sand and stuff like that. So you could go, so another wacky way of doing it, which is something we have done before, which is you do go propulsively all the way to the surface, but then you have to do something to modify the rocket engine nozzles to reduce the amount of pressure from the nozzle, to reduce the amount of erosion that you see. Or if you were a human mission, which is probably what you would use, retropropulsive all the way to the ground, you would have to create a landing pad, and so that landing pad would be made of something really solid. So that means you'd have to do it in advance, basically, so that you couldn't disrupt the vehicle by kicking up all that sand and things like that. But I'm trying to think, there's one more thing could you do, or you could also just cut off your engines, and you could maybe use sort of an aircraft system and glide into land. So that's another thing. That would be very wacky, which we haven't done yet, but which would be nice to do. And the thing that we're always pushing for is improved precision, so shrinking down that landing ellipse. So for a human mission, you'd pretty much want to shrink down the landing ellipse maybe to the size of this auditorium here. And the way you do that is by carrying more fuel on board, so you can fly out more of your errors to get to exactly where you want to go. And that video that I showed of the images towards the ground, of the final descent looking towards the ground, that was actually a technology demonstration for terrain relative navigation, where you're collecting onboard images, you're taking a look at the ground below and saying either I'm where I want to be, or I need to move a little bit to the right, to the left to get closer to where I want to be. So those are some things. So we always try and build in new capabilities with these missions so we can demonstrate them in a future one. And that is a capability which is actually going on Mars 2020, which is terrain relative navigation. That's already been baseline for it, as a result of us being successful with that demo on this one. So. Good questions.
I want to make sure that we end on time. So unfortunately, I'm going to have to take the last one, which will go to this gentleman back here. While the mic's going, have you guys talked about space elevators, lifts?
I don't think there's anything really going on, at least not in our area.
In the wacky side of things.
Yeah.
This is slightly related to the last question in that earlier you talked about diversity of ideas, and I wondered how much what other ideas on the sort of drawing board stage you came up with as a team for the recovery of the Curiosity mission and the sort of main deployment stage.
So we did. So I think our big trades were airbags, retropropulsive all the way to the ground, and Sky Crane. So those were kind of the three big ones that we did trade, and we made the decision for the Sky Crane just because it gave us the most landed mass and we thought was the lowest risk solution. So I don't think we really, another trade that we did do, actually now I'm remembering, is that we were trading having two parachutes, so where we would have a supersonic parachute and a very large subsonic parachute, which is kind of what you were asking, but because it's a subsonic parachute, it's able to be deployed with, you're able to do a real end-to-end test of that deployment here on Earth ahead of time, so you know that would work. We ended up not going with that, and the reason for that is because the problem you always have on Mars is you never have enough altitude, you never have enough time. And so when you actually do the trajectory calculations, because of the uncertainty and all these different properties, you didn't know if it was going to deploy here or here, because you're on this asymptote. And so because you didn't know that, you may actually run out of time to inflate, deploy, and fly the second chute. So we ended up going back to the first chute. We really wanted to do that. We actually spent money to qualify a big subsonic parachute, but we ended up not being able to do it because of the trajectory and the timeline and the altitude margins that we had. But yes, in engineering, all you do all the time is trades. You do trades up until almost a day of launch in different aspects, right? You do design trades, you do implementation trades, then you may do operations trades. But that's kind of how you do things so that you always optimize the solution for what you need to do next.
Great. I have a feeling we could go on all night, but
I might run out of juice.
Great questions. Thank you very much to the audience, and can you join me in thanking the speaker one last time?
Thanks for having me.